Hello, everybody. I hope you had a good weekend and that you had time during Saturday and Sunday to check the new homework, in addition to the lecture notes and video materials that I uploaded last week regarding the review. So today we're going to start the meat of our quantum mechanics 2 course, which is an introduction to time-independent perturbation theory. So the introduction will consist on showing you how to calculate the first order corrections to energy levels that are not degenerate and the related wave function corrections. So let me share my screen and we'll start in a second. Okay. So look, let's start. So again, in a summary, this whole section on time-independent perturbation theory, in addition of the objectives I described you just a second ago, we'll also learn how to find second-order corrections to non-degenerate energy levels, and also how to find first-order corrections to energy levels that are degenerate, and the corresponding zero-order wave functions which are good. I'll tell you what is good later on in the course, so just bear with me. And the last is basically an extra topic which I also think it's interesting, that you can interpret the non-degenerate case of time-independent perturbation theory as some sort of iterative method. So that's interesting, but that's the last part of the chapter. And so what is time-independent perturbation theory? You may have actually seen a technique like this in either an engineering course or perhaps some sort of fluid mechanics course. But in the context of quantum mechanics, let's say that you know the solution of an eigen problem of Schrodinger's equation for a simple problem, like say the harmonic oscillator or some other simple feature. And so in that problem, you would know the eigenfunctions and the eigenvalues for the simple problem. So then what time-independent perturbation theory lets you do is to, for a more complicated problem, find the new eigenvalues and eigenfunctions, at least correcting them up to given orders, okay? So what happens is that you add a small perturbation to the Hamiltonian versus the old one that you have. Then you will do basically a power series expansion where you have this perturbation parameter that will be expanded in a power series. And then you will match the orders of the expansion in this parameter. And that's what will let you find subsequent corrections of increasing order in this parameter. We might call it lambda later on. So there is an importance of the fact of the energy levels being degenerate or not, because that changes a little bit the algebra and how to manage this. So we will treat the cases separately between energy levels that are not degenerate, meaning that their eigenspaces are basically one-dimensional for each one, and degenerate, where basically for a given eigenvalue, you have an eigenspace of dimension greater than one. So let's see, what else do I have to mention? Well, yeah, I mean, this approach is time independent in the sense that you're dealing with the eigenproblem of Schrodinger equation. Um, so when you have this eigenvalue problem for Schrodinger, you have already taken out the time part and you're just focusing on the spatial part. So that's why it takes its name. Um, yeah, well, one last thing is that in the management of time-independent perturbation theory, we'll have this expansion parameter, but at the end of the day, we'll make it equal to 1. The reason why will become clearer when we see actually this interpretation of time-independent perturbation theory as an iterative method. I'll explain the technique mathematically, so don't worry about it, we'll make it clear. And yeah, I mean, I think that's the summary of the methodology. So let's start. I guess what you can say is that this is a mathematical technique applied particularly in the context of a quantum problem. In this case, it can be applied to other problems, but it's good to distinguish the physics from the math. Okay, so let's start. Let's say we have first order corrections to non-degenerate energy levels and wave functions, right? So we have the eigensolutions, which are non-degenerate again, meaning that the eigenvalues do not have a eigenspace, basically a space of dimension greater than 1. And you know, so the eigensolutions to Schrödinger equation for a given Hamiltonian, which might be simple or just might be known, right? And we're going to call it H0. So because you have the eigensolutions, you know the eigenfunctions and the eigenvalues, the energy eigenvalues. So, and again, by non-degenerate, we mean that two linearly independent eigenfunctions cannot have the same energy eigenvalue. So which is equivalent to say that basically the eigenspace for each eigenvalue is of dimension 1, just one basically uh, linear space of dimension 1 proportional to that function. And well, you also know beforehand that the sets of eigenfunctions are or constitute a complete set. What does it mean that it's complete in this context? It means that any function in the Hilbert space can be expressed as linear combinations of these functions. And so this is, or it can be made orthonormal, and we'll consider that this will be an orthonormal basis. Now, okay, so this is what we know. And we know simple problems for which we know the solutions. Those are, say, the ones from your previous quantum mechanics course. But our goal in our context is that, let's say we have a more complicated Hamiltonian or a new Hamiltonian, which is made of the previous Hamiltonian, H0, plus a perturbation. This perturbation is going to be called lambda H prime. So lambda is this perturbation parameter. We're just going to use it for the moment as some sort of control parameter, in the sense that it will let us keep track or order of the different orders of the expansion that we will do later on. So at the end of the day, we'll make it equal to 1. But think that basically you have a parameter that controls a magnitude, and then H prime, which is actually the perturbation Hamiltonian. So lambda is an expansion parameter that controls the size of the perturbation, as I mentioned. And what we want to do is to find now the eigenfunctions and eigenvalues for this new Hamiltonian. Bear in mind that there's a difference in the notation. For the old wave functions, they had a subscript or a superscript 0. So they were phi 0n. And here the new eigenfunctions are psi n. So, okay. We have new eigenvalues and eigenfunctions. So what are we going to do? Okay, we have this parameter that controls the perturbation. We're going to think, okay, perhaps what we can do is to basically make a power series expansion of the new eigenfunctions and the new eigenvalues in terms of the basically, how can I say, in terms of the parameter lambda, and then subsequent corrections to the eigenfunctions and eigenvalues. Because if you notice this is what's happening. So you have this expansion, again, is in terms of powers of lambda. The lowest order, meaning the power of lambda equal to 0, which is this one, is actually the old solution of the problem. So basically, in the limit as lambda would go to 0, you have the old Hamiltonian, and you would resort back to the known solution. So what you're doing is, okay, perhaps as I make the perturbation bigger by making the value of this parameter lambda bigger, the effects of the perturbation will be more noticeable. And so it kind of makes sense to make this expansion. So the expansion is identifying that the perturbation will affect the how the true eigenfunctions and eigenvalues are constituted. And also, most importantly, what you notice is that you have subsequent corrections at each time. So this is the correction basically at order 1. Remember that we will make this parameter lambda equal to 1 at some point. Then this is the correction of order 2 because it's related to the power lambda squared, and etc. So you could have this expansion, right? If you make at the end lambda equal to 1, well, I mean, this will be the first order correction, the second order correction, and so on. But it's good to keep lambda for a good amount of the calculation, precisely to keep order or keep track of the order of the corrections. Okay, so there are some things that we must keep in mind. The first one is that, okay, you're doing a perturbative expansion. And well, when are you justified to do this perturbative expansion? Heuristically, you're justified by assuming a small perturbation. So the expansion parameter or should be small, right? So expansion is valid for small values of lambda. Now, again, as I mentioned, when lambda is equal to 0, there is no perturbation, right? And so you would go back to the old solution, which is actually the lowest order. So it is when lambda is not 0 that you start getting corrections to the eigensolutions, meaning to the eigenvalues and the eigenfunctions. And so usually it is enough in quantum mechanics to stop in second order corrections to the energies and uh, yeah, I mean, first or second order corrections to the wave functions. So, okay, let me drink some water. And again, there is a notation for the corrections. If you notice, okay, the n corresponds to basically the energy level and the nth energy level, for example, but the subscript 1 or 2 or 0 means basically at which order of the correction you are, right? So this would be the first order correction because you have the old energy plus this term. Then this is the second order correction and so on. I mean, approximately, basically, if you truncate the series, the new energy will be the old one plus this first order correction plus this second order correction. Again, remember that we will make lambda equal to 1 at the end. So, okay, this is nice. This is actually a common perturbative method in engineering and physics. And so what will you do? Well, you have these ansatz somehow for the energy values and the wave functions, and you have the new Hamiltonian, right? So what you're going to do is to plug in these expressions in the Schrodinger equation for the new Hamiltonian, right? So, well, for the eigenvalue problem of the Schrodinger equation in the new Hamiltonian. So let's do it, right? So we plug in new Hamiltonian, uh, wave function expansion uh, in a perturbative expansion with the parameter lambda. So this is a shorthand for this. This would be equal to, well, the Hamiltonian to the new wave functions is equal to the new energies times the new wave functions. So that's why you have this multiplication of expansions. And well, um, basically expanded out, it would be like this. And what is going to happen? Okay, I have basically power expansions in each side of the equation, and I'm just going to match the terms because the terms should be equal, right? So we have two equal power series in lambda, and so we'll equate terms of the same degree. And by keeping or looking at these equalities for different degrees of lambda, we'll obtain different equations for different orders. So you'll see what we have. So, well, the first term, basically, what you notice is that this is increasing the degree in lambda by 1, right? And so there is basically one single term in this side of the equation that does not depend on lambda, which is this one. Then you have the expansion where basically H naught is an order lower, or how can I say, because this contributes by power of lambda. So you have lambda j, then h0 to phi jn, but h prime is to phi j minus 1n because of this, okay? So, well, if you were to go to the quality, you have to go to the multiplication of these two series in lambda. This is just another way to basically make multiplications of series. You may have seen this in your class of ODEs, or, well, if not differential equations, perhaps in methods of mathematical physics or a class like that. So this is the way to multiply series. And, well, again, there's going to be one single term that does not depend on lambda. And then for each ordered in lambda, so you have powers of lambda, lambda 1, lambda 2, etc., etc. This is basically the factor. So you have the sum of k, j, e, k, n, psi, j minus k, n. So you will see when we do the concrete cases for j equal 1 and j equal 2 that they look quite as what you would do when you have basically a polynomial multiplication. In this case, it's a series. So what is clear from here is that in the lowest order, what you have is h naught phi 0 n equal to e 0 n times psi 0 n. And so this makes sense because this is actually the equation that you know. I mean, this is the Hamiltonian for the old problem with its old energy values and its old wave functions. So this is in a way a sanity check which should hold for consistency. So this is just the eigensolution of the old Hamiltonian. Clearly at the lowest order, let's say when there's no perturbation for lambda equal to 0. So it's just a good sanity check of that our method is working for consistency with the old problem. Okay, it doesn't need to provide me information. It's just making sense at this point. So this is the sanity check. We're good, but again, this is not providing new information. But let's go to the higher degree. So you would have to go to basically j equal 1, the term for j equal 1 plugging in over here, and then substituting, say, for j equal 1. So the sum from k 0 to 1 of ekn phi j minus kn. If you do that, well, here, yeah, it's kind of clear what we would have, right? So plug in j equal to 1 over here, and this is the term that we expected. So the old Hamiltonian to phi 1n, the perturbation to phi 0n. And here again, we would have this expression. If I plug it in, I get E0n psi 1n plus E1n psi 0n. This looks like what you would get from a multiplication of polynomials, which happens also in the series up to a, well, certain degree. And so the second order in lambda, if you basically monitor now lambda squared, so j equal to 2, again, you would have the old Hamiltonian applied to phi 2n plus the perturbation applied to phi 1n. So this is coming from here. And here what you would have is basically the sum from k equal to 0 to 2 of these terms, ekn psi 2 minus kn. Again, very similar to what you would have in a series multiplication. So there is some sort of balance in the indexes if you notice. So you get E0n psi 2n plus E1n psi 1n plus E2n psi 0n. That is expected. So in principle, you could do that for the higher orders, but again, in quantum mechanics, you rarely go past second order. So again, it is to be mentioned that you care for a perturbation with value equal to 1, meaning that you will make lambda equal to 1 at the end. And usually in quantum mechanics, it's understood that lambda is some sort of artifice to keep track of the powers. So keep it in mind. I will give a little bit of further explanation in this at the end of the chapter, but just bear with me right now. So just keep it in mind that we'll leave it at lambda equal to 1. So, okay, let's go to the first order equation, right? Which is what we have here. So we have assumed that the energy levels are not degenerate, and that will become evident in a second why we need that assumption. But in any case, in the first order, we have this equation, right? So, okay, what we want to know is basically these terms, phi1n and E1n, which are the first order corrections to the wave function and the energy. We'll get first the first order corrections to the energies. So how will we do that? So to obtain the first order corrections to the nth energy level or eigenvalue, we just have to take inner product with respect to psi 0n. So let's do that, right? Basically, where we would start would be from here. Um, this is constituting the inner product with respect to phi 0n of this term. If you go on this side, basically you're using linearity, then you're using also basically Hermitian properties on this part because you pass the H0 to the other side. This is convenient because this will pull out the energy level N, which is real, so there is no issue with conjugacy over here, and this gives you this term. The other is just the same term that you obtain after applying linearity. And now on the other side, while you're applying the inner product, uh, this one is easy because on one hand, you have constants, some of them come out. Well, of course, you applied linearity before. And then this will just be the inner product of phi 0n with itself times E1n. So because of orthonormality, you have a factor of 1, and that's why you only get E1n plus E0n. And then you have the inner product of phi 0n with, sorry, psi 1n. I'm sorry if I forget sometimes um, to, to use the right words for the Greek letter. So comparing terms, we have the new information provided is basically this. So yeah, I mean, you only have to basically pass to one of the sides, and this term will cancel with this one. So this is basically saying that the expectation value of H prime, which is the perturbation Hamiltonian, uh, when you are in the wave function phi 0n, is the first order correction that you were looking for. So if I were to restate this, the first order correction to the energy, which is this, is the expectation value of the perturbation in the Hamiltonian. Remember, we will make lambda equal to 1 at the end for the unperturbed states because these are the wave functions of the old Hamiltonian. So this is what you're meaning. And this is an important interpretation of what is the first order correction. So just keep it in mind. So we have the first order correction to the energy. What are the first order corrections to the wave functions? And this is where the non-degeneracy becomes important. So let's say we would go back to this equation, right? And in this equation, what will happen is that you will split terms, basically put on one side the terms related to psi 1n, and on the other side, the terms related to psi 0n, okay? So, well, at this point, you know uh, psi 0n because those are the solutions of the previous problem. You in principle know H prime, at least in its math formulation. You know E0n, you know H0, because those are basically, that is information of the previous problem. And the thing that you want to know is psi 1n. So, well, basically what you have is everything is known except for psi 1n. This one we just obtained 1 second ago. So you want to obtain psi 1n, and you can interpret this basically as some sort of inhomogeneous differential equation for the first order wave function correction, because everything else is known, and you have these basically DFQ operators. But well, the interesting thing is that also the old set of eigenfunctions is a complete set. Because it's complete, it can represent any function in the Hilbert space by linear combinations, in particular the one that we're looking for. And so we can propose basically the first order correction as expressed in terms of the old eigenbasis. And so these are the notations for the coefficients at this point. Notice it. So n is fixed. Then you go over all the indices of the eigenfunction, which m is taken care of. And you'll notice why n is being excluded. And so this is done because going back to basically our first expansion of the full new wave function, because this is just a correction up to first order. So you have the new wave function will be the old one plus the first order correction times a factor of lambda when we don't make lambda equal to 1, plus the second order correction times lambda squared, etc. And so basically what you're trying to do, you're getting an expression of the new wave function in terms of orthogonal functions. So let's say, for example, take lambda equal to 1. So you kind of like don't want to put all the information which would represent this term into this new term, because you already know that this wave function has a component in uh, psi 0 n. So you would like to exclude it because this term is taking charge of basically the component along psi 0 n. So in principle, you wouldn't need to add it. Another way to say it is like, think of it as if you had vectors, right? And so you have a new vector, which first has a component along this one, and then you're adding new components. So why would you add, again, basically a component along this direction? So this is kind of like some sort of Gram-Schmidt procedure where you're introducing the new component, and so you have avoided to add the old components by some sort of orthogonalization. So again, so you omit the n term in this expansion because you think basically uh, of psi n in terms of orthogonal functions. And so the subsequent term should have no component in terms of psi 0 n. If it had one, and so this is the important point, if it had one component, you could combine it just with the previous one, in the case lambda equal to 1, for example, um, for the expression of psi n, and then remove it. So you could pass it basically, and then this would have nothing. And again, this is equivalent to some sort of Gram-Schmidt orthogonalization where you have a new vector in terms of a first component, then the new component should be orthogonal to the previous component, and that's why you don't have a coefficient or the coefficient is equal to 0 for the case m equal to n. And that's why you only need to consider this case m not equal to n. This is kind of gist of why we're omitting that term. And now you can solve the DFQ for psi 1n by finding this coefficient. So what you will do is to basically plug in the expansion, right? So you use this expansion, you substitute it in here. So what you will get is basically an equation in terms of the old eigenfunctions. So if we do that, well, this is coming from the plugin of this expression. Here you have this. And well, this is just basically applying the Hamiltonian operator of the old problem that you know to this function. So this comes out by linearity, then you have E0m minus E0n, and so on. So this term is coming from this applied to this. And so now what you can do is take inner product with respect to basically say a given element in the basis of the old basis, psi 0L, right? So if you take that, well, you have an orthonormality condition, and that's why you have the Dirac delta in this case. So this will be delta Lm due to orthonormality. This is just the inner product of this expression with psi 0L. And then you'll have the inner product of this side. So again, you're using linearity, you have H prime, psi 0L, and then with psi 0n, then you take the E1n out and you have this. So well, let me explain two different cases, right? So let's say that L is equal to N. That would mean that basically because M is different to N and L is equal to N, then all these terms would be zero because of the Dirac delta, sorry, the Kronecker delta. And well, in that case, you basically get something that you already knew, because this would go back to this equation, since in the case L equal to N, this would basically be equal to 1, and you go back to this. So it's just a restatement of the first order correction to the energies. So nothing new. So it might be worth to rather study the case L not equal to N. So that will be convenient also, because at least one term won't vanish here. And again, now why the energy spectrum being non-degenerate is important will show. Because look, basically, let's say that L is not equal to N. So it means that there is one M, which is basically L, which is not equal to N, for which this won't be zero. So this is the surviving term over here. Now, L is not equal to N, so this term will vanish. This one, sorry, this one. And you have this other one, right? So surviving term equal. And what you wanted is basically to find psi1n, which is given by the expansion in terms of the old eigenfunctions. And it suffices to know this coefficient C and M in order to know what is the first order correction to the wave energy function. Well, in that case, basically you only need to pass to the other side to get the coefficients and therefore get psi1n. But, and again, this is why the non-degeneracy becomes important, because, okay, now you pass it and it's dividing, right? So you have by just, okay, well, what I'm doing is basically calling M or LM in this case, so it's nothing different. And we know that M is not equal to N, which is by assumption over here. And again, we have this difference between the energies in the denominator. And so this is why the energy spectrum not being degenerate is important, because if it was degenerate, there could be the possibility of having different eigenstates with the same energy. And that would show, if the spectrum was degenerate, there could be the possibility that you have the same energies for different states, and this would be zero. So that's where it's important. So the minus disappeared because we basically made a change in the sign over here. And so this is the first order correction in terms of the complete set of unperturbed eigenfunctions, because I only need the coefficients. I have gotten the coefficients in here. I just need to plug them in. And so this is the expression of the first order correction to the wave function in terms of the old eigenfunctions with this coefficient. And again, showing again that the energy spectrum not being degenerate is important, so that this denominator is not zero and you don't have issues. That's the whole importance, and why we treat the degenerate case as a different case from the non-degenerate case, okay? So again, just stressing that we have made the assumption of non-degenerate energy levels for the unperturbed problem. And yeah, showing the importance of, well, okay, yeah, this is also an important point. So the last two equations also point out why it was important to express psi1n without psi0n component, because, well, there could also be the case where um, if you had taken the case C and N, then you would have a case with the denominator zero, and then you would also have issues. So we have prevented ourselves by basically excluding by this sort of Gram-Schmidt argument of orthogonalization, um, to exclude this singular case. So M is not equal to N, so you won't have this issue if you notice. And so you have this expansion with, well, in principle, well-behaved coefficients for the first order correction to the wave function related to the nth eigenvalue. So try to make a second review of the calculations at home if you can. So the last part is basically to show you an example of how can you apply first order non-degenerate perturbation theory. And so we're gonna basically show a simple problem where we have the harmonic oscillator plus a perturbation, okay? So the problem is the following. Consider the physical situation of an anharmonic oscillator with the Hamiltonian p squared plus m omega squared x squared over 2 times 1 plus x squared over b squared. So if you were to restrict only to this term, this is basically a harmonic oscillator. So the anharmonic part is coming from this. And you can split up the Hamiltonian again in two parts. The H0, of course, is going to be basically our old friend, the harmonic oscillator, which is taking account for these two terms. And the anharmonic perturbation is basically this times this. So you get m omega squared x to the fourth power divided by b squared divided by 2. So this is going to act as a perturbation. Um, so let me drink a sip of water. The first indication is to find the first order correction to the energy by perturbation theory. So we know this formula. This is what we intend to use, right? So the first order correction to the energies are basically the calculations of the perturbation Hamiltonian or the expectation value of the perturbation Hamiltonian in the unperturbed basis, okay? So that's why you have H prime averaged with respect to 5, 0, n. So that would be equivalent to basically using the eigenfunctions for the harmonic oscillator to take expectation value of x to the fourth times this other factor, which we have here. And this is what we will intend to do. And again, 5, 0, n are basically the n harmonic oscillator eigenstate functions, which we already know by, okay, playing with the ladder operators, etc., etc. You start with the basically ground state and you increase and so on and so on. So yeah, there are some normalization constants, of course, related to the effect of the ladder operators, or the racing operator in particular. And what will be useful, because think about it, we have to calculate the expectation value of x to the fourth. So it will be useful to express the position operator in terms of ladder operators. This you already know. Basically, if you add uh, the lower operator with the racing operator, and then you have the factor, you can get x. So x to the fourth would account basically to this operator to the fourth power. So that's why you have this squared. And then you have basically square the square to account for the fourth power. You can basically make, well, this is making the multiplication of a squared with itself, or a plus a dagger with itself, or squared with itself. Yeah, okay. So there is something important to mention over here in this calculation, which is that, okay, we want x to the fourth, but we can have this long expansion coming from basically raising this to the fourth power, but not all terms will survive. Because the reason we did this was because seeing x as the effect of combinations of raising and lowering operators will have a long expression here, but only the one that, when applied to phi 0n, goes back to the nth state will not be zero when taking inner product with n. If you basically, so this will have many terms. And after you, okay, one of the terms, let's say that actually has as a final effect, raising the state n by 1. Let's say that you would end up with a term with n plus 1. When you take inner product with the nth state, that is going to vanish. So again, only the terms in this basically state, effects to the fourth applied to the end state that are basically proportional to the end state will survive. So terms from the x fourth operator generated by this is the form of the terms that will survive, basically. So that, well, generated by AQ times A dagger 4 minus Q, that makes sense because these are the terms that will come up from the expansion of x to the fourth like this. And so that the raising and lowering renders us back to a state proportional to 5%. So basically, again, that the effect is that you get back to the nth state. So this is where we have made the splitting. So this accounts for this factor. Then you have basically, how can I say? We're using a notation where we're calling A dagger A minus and the other A plus. And these are such that, well, these are the bounds for the indexes, so that makes sense if you're making the expansion of this to the fourth power. And this will be the term such that combined effect is zero, at least in terms of where the nth state is. Of course, you will have proportionality constants, but if the effect is at the end to basically stay in the same energy state, you will be fine. So that's why we care only about terms where the addition of these powers is equal to zero. And these are terms that are non-contributing, because when you take inner product, uh, it will basically become zero. So again, just keep mind of this. This is a very temporary notation. I'm just trying to express how this net effect zero is related to this balancing of raising and lowering operators. And if you look for all these terms, basically this would be the ones that have net effect zero. So you have two applications of the raising, two applications of the lowering operator, two applications of the raising operator. Here basically also two and two, but in different order. So this is considering for all different ways in which you can apply the raising and lowering, but at the end having a net effect zero. So you have A dagger, A dagger, A dagger squared, A dagger, A squared, A dagger, and so on. So all the others where basically there is more A dagger than A or more A than A dagger will raise the state to a different level. And when you take inner product, this will be zero. So that's why we're doing this. So the calculation might look cumbersome. And so what we're doing is we're trying to avoid a little bit of work by just identifying what we care about, which is basically meaning these terms. The problem is not trivial, but that's why I'm showing it in class. Because if you learn at least the gist of a complicated problem, you might be able to do by yourself simpler problems, okay? So, okay, this is another basically nice trick that you might be faced to use in this problem, which is basically, if you were, you have, okay, the X representation and the P representation, right, for position and momentum. If you were in the raising operator representation, the way the lower operator would look like is basically partial derivative with respect to a dagger. I'm not sure if you have seen this or not, but we can make a very quick proof. So the effect of operating with A is equivalent to take a partial derivative with respect to A dagger. And the short proof, and again, showing a complicated problem to basically let you deal with the simpler ones. This is because, okay, you have A in terms of basically position and momentum. This is a quantity proportional to momentum, y equal to P over m omega. And a dagger looks like this with the minus. And so if we were to basically analyze the partial derivative with respect to A with this representation, and well, it's a complex derivative, so it has to satisfy Cauchy-Riemann conditions by complex analysis for being a nice or well-defined partial derivative in the complex plane. So you would have partial with respect to A, which is this. So you have the proportionality factor over here. And so you can decompose in the real and imaginary parts of this. Then basically what you're going to do is to apply Cauchy-Riemann conditions. And that would render you basically, let me go back to this part. Yeah. That would render you with this operator. So this has come from the application of basically Cauchy-Riemann. And so the representation would be dx minus I dy over 2 square root of m omega divided by 2 h bar. Also, if you were to analyze the complex derivative with respect to a dagger in the complex plane and applying Cauchy-Riemann conditions, you would have partial derivative with respect to x minus ey. Then this factor is coming out from here. So you have the real and imaginary parts. Again, this is Cauchy-Riemann. And if you were to do the algebra, you would have this. So dx plus I dy divided by this factor. And now you know that P is in the moment, in the position representation minus I h bar partial x, and x is equal to I h bar partial P. So A, you can represent it like this over here. And so basically by identifying what is y in terms of P, you get that A is equal to this square root of this term times I dy plus dx. And if you go back to the identification, basically this is where you get that this is equal to partial derivative with respect to a dagger. Okay, so this is a short sketch of the proof of why you would get a equal to partial derivative with respect to a dagger, the representation. Why are we doing this? Okay, this might not seem clear at the beginning, but there's a reason. And the reason is that, well, I will have the x to the fourth operator. These are the interesting terms, okay, which I will have here. And well, if I include the partial derivative with respect to a dagger as substituting for a, many things will balance out. Essentially, I will get lowering powers over here and decreasing the degree of a dagger also when I apply this operator. And you will get simpler terms essentially, instead of having to know the application or what is the effect of the application of the a dagger many times. So let's look at the terms. We have this expression coming from here, basically the terms that have net effect of not raising or lowering the state to a different energy. Then if I substitute for a dagger, I have this. And what will come up is that you have to apply the partial derivatives with respect to this. So this is just like a calculation in calculus, right? Of taking derivatives of polynomials. And so, well, here what I did was substitute basically phi 0n in terms of the expression in the ground state and the raising operators, because I will have to analyze the effect of applying the partial derivatives with respect to a dagger. So that's why I need to use this formula. And okay, I will have that. Basically, if I do that, well, for some of the cases, you can actually apply beforehandedly the partials. That might not be necessary at this point. I think I might even have a repeated line over here. Let's see. Okay. Yeah, I think it's repeated. Yes. Yeah, I think it's okay. And is this one also repeated possible? Yeah, I think so. Okay. So if you were to do that, basically think of it. Think of a dagger just as, say, the variable and apply the partial derivative as needed. And well, if you apply it, for example, 2 times over here for this term, you'll have basically n times n minus 1. And then it would seem that you have lost um, 2 a daggers, because you would have a dagger to the n minus 2. But then with this multiplication, you're back to business. And so that's why you get this term and you recover, right? And then basically we have gone back from 5, 0 to this and then back to this. If you were to do this, for example, monitoring this term, you would have partial squared of a n plus 2, right? So that's why you have n plus 2, n plus 1, okay? And so on. I mean, this is basically you raise a dagger by a power. That's why you have n plus 1, then take derivative, and then you do that 2 times. So that's why you get n plus 1 squared. This one basically explains why you get n plus 1 over here. And basically, then you would have n, and so on. Let's see. Okay, you can do the verification for these 2 terms on your own. But let's see what else. Okay, if you were to do this, this shows why the approach of using the a in terms of a dagger was simpler, because, well, we were lucky enough for this was a very nice trick in order to avoid basically a strong calculation. And you got the effects of these operators, or effects to the fourth in particular, by basically taking derivatives. And what you are missing to do is simply do this addition of terms in n. If you were to do this, you have 3 plus 4 to the n times n plus 1 times n, well, plus n times 2n minus 1. And simplifying, this is what you would get. And let's go back to where we were, right? Okay, so what we wanted to get was basically the first order energy correction, which is the multiplication of this factor with this term. This is the term that we just got. So we just need to multiply this expression by the factor m omega squared divided by 2b squared, which is what we have here. So, well, perhaps we can do a further simplification. Let me see. No, I don't think so. Well, I mean, just, you know, basically taking this square and you're done. So this is nice because this has been a nice technique or a nice trick in order to let us calculate the first order energy correction for a complicated problem. And so we have that the energy eigenvalues up to first order are, so this is approximate, of course, because we're doing this power series expansion and we usually do not go beyond second order. So you have that the new energies are approximately the old energies plus the first order correction term. So these are the old energies from the harmonic oscillator that you already knew. This is the correction term. Now, if you were to combine some of these terms, you could get this equivalent expression. Why are you doing this? Well, because of the next problem, which is that, okay, you have the new energies. Now you want to identify the change in the frequency introduced by the anharmonic perturbation above. And also the anharmonic oscillation introduced by examining the energy levels. So we have this result, okay, which is basically coming from here. And we would like to, well, interpret a couple things. First of all, identify terms proportional to n plus 1/2. Okay, so one of them is coming from the old harmonic oscillator frequency. The other one, if you basically, you will get an n plus 1/2 because, well, you have 2n times n plus 1. So basically this pair of terms will account for n plus 1/2 multiplied by a factor of 2. And this will be another contribution. So you can look at this in this expansion. So what I'm basically doing is dividing by 1/2 this term, or passing the factor of 2 over here. So that's why you have 3/4. Then you have this, and then you have n plus 1/2 plus n squared. So this is basically 1/2 coming from the passing of these two factor. And so this lets you identify um, the factor of n plus 1/2 over here. So what you would have is En equal to n plus 1/2 h bar omega plus delta omega plus this. And so this is nice for the following. So for the harmonic oscillator, the frequencies were of this form, right? What you're doing when writing the term in this fashion is basically expressing the changes in the energies in a couple ways. The first one is a change in frequency, and that's why the factor of n plus 1/2 was important to express. So this is saying, okay, you have the new energies are like the old energies, but there's a shift in the frequency on one hand. So, but at this point, it doesn't explain or show an harmonicity, it just shows a shift in frequencies. The harmonic part is basically this one. So, okay, you have a shift in frequency and also basically a term that somehow cannot be explained by the harmonic oscillator, right? Because the harmonic oscillator is explaining that the energies are proportional or basically linear functions of n. In this case, this is n squared. So clearly that is a not harmonic effect. And so again, identifying the shift in frequency is one part. So we have it here. And this is the non-harmonic part. And again, the non-harmonic or anharmonic perturbation increases the frequency by delta omega. Okay, so that is one of the effects of our perturbation, of course. And it makes the spacing between levels increase with increasing energy due to n squared h bar delta omega. So this is this other effect, okay? And so this is the term that is identifying oscillations that are harmonic, precisely because, again, energies are usually linear functions of n, but this is quadratic with respect to n. So this is the term that makes it more evident that you're having non-harmonic or anharmonic effects. So hope this helps. So this is accounting for the first part of basically time-independent perturbation theory, where you have non-degeneracy in the energy levels with the theory presented before and a simple example for the correction to the energies up to first order. In the next class, we will talk more about second order corrections to non-degenerate energy levels. And later on, we'll also talk about first order correction to degenerate energy levels and to the corresponding zero order wave functions. And then at the end, I will clarify a little bit of why we make this lambda parameter equal to 1. I think that's a part that if it's the first time you see perturbation theory, particularly in the context of quantum mechanics, it's not clear, or like, why the big fuss about lambda if you're going to make it equal to 1. So that has to be commented in more detail. For the moment, this is just an introduction to basically get you presented with the gist of the theory, how the calculations are managed, and so on. But hope this was clarifying. I will be having office hours as well in case you need any help, either with the previous material or the new one. And I will post the homework at the end of this section. So we still need 3 more subtopics to get you to the new homework. But in the meantime, try to read the notes, study the textbooks, do some problems on your own, and I'll be happy to help you during office hours if you need. So have a good week and glad to see you soon.